Hello and welcome to my YouTube channel. Today we are going to design a project in which we will be measuring the temperature of our environment using temperature sensor and STM32F44 6RE microcontroller board. This is the part 4 of the series where we are basically discussing about the applications of analog to digital converter and their applications. So let's start the video. First of all, let us talk about LM35, which is basically a temperature sensor IC, and we'll be using this IC to design our project. So before designing a project using LM35, we must know few details regarding the LM35 temperature sensor. First of all, this IC provides analog output and it is linear in nature. That means it provides a linear voltage output which is proportional to the temperature or the surrounding temperature. Secondly, the range of temperature which the IC can measure is between -55 degrees Celsius to 150 degrees Celsius. It has an accuracy of ±5 degrees Celsius and it consumes 60 microampere current generally, depending on the voltage source that you have applied, but in general it consumes somewhere around 60 microampere. Remember, the output voltage of this IC increases linearly with temperature, so we don't have to do a lot of calibration in this IC because it behaves linearly. And calibration, when we talk about calibration, the output voltage directly corresponds to the temperature in degrees Celsius. Therefore, we don't have to apply any equation or mathematical equation to calibrate the IC. Now, one very important feature of this IC or any temperature sensor IC is the temperature coefficient. LM35 has a temperature coefficient of 10 millivolt per degree Celsius, which means for every degree Celsius change in the temperature, the output voltage of this IC will vary by 10 millivolt. Remember, each degree Celsius change in temperature will bring an output voltage change of 10 millivolt. And it is easy to use and it has got variety of applications, especially when we are talking about measuring the temperatures. Now let us briefly talk about some of the equations which we must know if we are dealing with LM35 or any other temperature sensor. Generally, temperature sensors provide you output voltage which are given by Vout equal to V0 plus T plus temperature coefficient, where V0 or V0 is the output voltage at 0 degree Celsius. T in general is in degree Celsius. Temperature coefficient, for example, in case of LM35 is 10 millivolt per degree Celsius. So if you are going to use any other linear temperature sensor, then do check what is the temperature coefficient of that temperature sensor. Otherwise, we will be making small mistakes. Now let us talk about the calculation. So to find the temperature T from the measured output voltage, we can use this equation where T is equal to Vout minus V0 divided by temperature coefficient. Here in our example, temperature coefficient is 10 millivolt per degree Celsius. V0 is 0 volt, that is 0 volt at 0 degree Celsius. So therefore, T comes out to be V0 upon 0.01. For example, if V out, that we are capturing the voltage, is 0.35 volt at our microcontroller's ADC, then temperature will be 0.35 divided by 0.01, which is approximately 35 degrees Celsius. Now let us see the connection part. So for the connections, remember we have this LM35 and the microcontroller board. The leftmost pin of the LM35 should be connected to 3.3 volt, or depending on your microcontroller board, 5 volt, because in our case Nucleo F446RE is having a 12-bit microcontroller, 12-bit ADC. This 12-bit ADC can range between 0 to 4095. Okay, and therefore 4095 in our case is represented by 3.3 volt and 0 is represented by 0 volt. Therefore, in our case we are connecting it with 3.3 volt. Now after that we have to connect the central pin, which will provide the analog signal, and we will connect it to the A1 pin of the microcontroller board. Then we will connect the ground pin to the ground pin of the microcontroller board, and this is all we want in the connection section. Let us after connecting the board, we have to write the code, or we have to develop the project. So let me start the STM32 Cube IDE, and we can go to new STM32 project, and this will take few seconds to upload all the necessary files. And like in our previous examples, we will start with CubeMX perspective, and then we will write our code in the C perspective. So first of all, we will come across this CubeMX perspective. So let us first select the microcontroller board. So for that I will use F446RE microcontroller board. Okay, and then click next. Let us give a name to the project. So let us give a name temperature underscore sensor using LM35. Okay, and then click finish. So initialize all peripherals in their default mode. No, we don't want the peripherals to be initialized in its default mode. Then after that we will enter in the CubeMX perspective. It will take few seconds. So here we are with the CubeMX perspective. So first of all, let me go to the pin out, clear pins. So this will clear all the pins. Click yes. So now we have the bare IC with us. Now let us go to the system core, go to system, trace asynchronous. This particular configuration you don't have to follow, but in general it is safe to do this. Okay, now after this we have to use the ADC1, and we are going to use A1. So let me go for in1. Here you can see after enabling the in1, ADC1 in1 has been enabled. And for the details you can just slide these windows and check. We are using 12-bit ADC, and rest of the things we are not going to change anything. Just enable the ADC1 in1, that's all. And then click on Either you can go for save all, or you can click code generation gear. After this, you will get all the necessary codes and initialization codes. Here we have to start writing our code to read the micro temperature sensor and get the value of the temperature sensor. So let me start writing the code. We'll be following almost the same steps which we used in our previous projects. So let us first declare some values. So we can go here. Okay, so we can go for hash define. Let me go for ADC underscore resolution, which is the resolution of our microcontroller. So it's 4095, which is 12-bit ADC. Then we have to use hash define v underscore ref, which will be the reference voltage, which is 3.3 volt in our case. And let me define temp underscore sensitivity. This variable will hold the temperature coefficient. In our case, it is 0.01. Okay, and then we are going to go for averaging the values, because otherwise we will get fluctuating values of the temperature. So we will be taking a number of samples and then we will be averaging them. So define number underscore samples. So suppose we are going to take 10 samples from the ADC and then we will average them out. Okay, after that we have to declare some variables: voltage, temperature, and ADC value, and then average temperature. So these are our variables and we have declared all the variables. Let us go to the coding section in the while loop. So we will come to the main and then we will go to the while loop, where we will write our code in this area: user begin 3 or user code begin 3. So if you do not write the code in this region, okay, or any user area, in that case, whenever you will make any changes in the CubeMX, all your codes will be deleted. So we have to be very careful and we should always keep our codes within the user code area. So let us start coding. Hall underscore ADC control space. I can go with start, which we were doing in the past also. Okay, we'll use this handle. Then we will use the polling. So hall underscore, which this code we have already used in the previous examples. Okay, so polling for conversion. And timeout, let us use a small timeout of 5 millivolt. Okay, which is more than 5 milliseconds, sorry, which is more than sufficient. And then we will take this reading in the value or variable ADC underscore value. So let us read the value of all underscore ADC underscore get value. Okay, pass the handler and then convert the value that you have received from the ADC to its equivalent voltage. So voltage is nothing but ADC value multiplied by V ref, okay, divided by Let us typecast the ADC resolution. Let me check ADC resolution. Something missing here. We have declared ADC resolution. Yes, we have ADC resolution. So let me copy and paste it here. Done. And then let us convert the voltage that we have received to its equivalent temperature. So temperature is equal to voltage divided by temperature sensitivity. Here we have temperature sensitivity, semicolon, and then we can stop the ADC. So for that, all underscore ADC underscore stop. Okay, we can use the handler, and then we can have a small delay. So delay of suppose 500 millisecond. So this is all we have to do. Now let us go for the conversion part. So this is all you need to do, but if you want to do the averaging of the temperature, then in that case we have to add some more lines. For that, let us declare float. Let us first upload this code and see how this code responds. Then later we can modify the code. So first of all, let me build this code. And we are getting some errors here. So it says we are missing some value here. Define vref 3.3. Is there any error in this section? Let me check. Expected as semicolon. What's wrong here? My mistake, we don't have to use any semicolon here. Okay, let us rebuild the project. So 0 errors, 0 warning. Okay, now we can start debugging. So for that, click here on the debugger and click OK. And here we can go for live expression, and here we are reading 3 different variables: ADC value, temperature and voltage. Right now we are not doing any averaging in the code. So let us see here. You can see the temperature right now in my room is 25.3 degrees Celsius, and the ADC is reading a value of 317, approximately 316-17, and I am getting a temperature of approximately 25.5 degrees Celsius. So let me just start the camera. So here we have the temperature sensor on the breadboard, and let me cover the temperature sensor with my finger, and we can see the temperature is rising. So now right now the temperature is 29 point or somewhere around 30 degrees Celsius. And if I remove my finger, the temperature will change and it will come back to the room temperature. So with this, I would like to end the presentation because it is already a lengthy presentation. In the next video, I will show you, or I will just modify this same code, take average of the temperature so that we will not see a temperature which is varying randomly or in a very fast manner. With this, I would like to conclude the presentation. If you have not subscribed the channel, then I would request you to please subscribe the channel. If you have any doubts or suggestions, please share your doubts and suggestions in the comment section, and please press the bell icon so that you can get the notification as soon as I upload a new video. Thank you and have a nice day.